So yesterday we wrote code that said we're going to put a queue inside of an array. And the way that we did that was we said, well, we'll keep track of where's the next thing that we want to take off the list, and we'll keep track of where's the next free place where we're going to put stuff. Okay? And the sneakiness to this one was to just play the simple trick of when you get to the end, we'll just wrap around to the beginning again and start using any unfilled slots that are available at the beginning in order to put stuff in. Okay? And that's the little trick that makes that thing work. The only problem with that is that that assumes a fixed size queue. So this would be a good one on the constructor to provide an argument to people to say, here's the size of the array that I want, and then maybe have some check to make sure that that they don't overrun each other. Okay, someplace in the code throw an exception if they happen to overrun each other, so somebody knows that they're trying to put too many items into the queue. Okay, but that one's sort of fairly straightforward once you get that bit of sneakiness. Okay, so the next task is to say, well, suppose instead of storing it into an array, we wanted to put our queue into a linked list. So here's an example of a queue in a linked list. So if I want to get the first thing out of my queue, the thing that was added the earliest, how do I go about doing that?
Get the value that's in the head.
It's right at the head of the list, and then what? How do you remove it?
And then you set the head to the a.next.
So just slide head over, so head equals head.next, which is just like advance the head by 1, and that makes that one go away. Okay, so that's a simple piece of code to remove it. How about adding E?
You need to keep track of where the tail is.
Well, the problem with this thing is that in order to add something on to the end of what we've got, it's always inefficient because you always have to run through all of them in order to get to the end. Okay? So that's not a good way to do it because that's really, really bad performance if this thing gets really long. So the trick to this one is to add a tail pointer and play that game. And now with that one extra piece of information, you always know where the end is, so how do you add to the end?
Tail.next.
What's the first thing?
Equals E.
Make a new node that refers to whatever thing you're trying to store, then tail.next equals new thing, and then bump the tail. Okay? So let's write the code for that one. We'll go in here and we'll make a queue with a linked list underneath. And it's going to take E-type things, and it's going to implement queue interface for E-type things. Okay. To our friend the bulb to add the unimplemented methods, and now what? What are we going to keep track of?
Head, tail, and side.
And let's just see if I can steal the node class from something else. So there's the node class. We'll drop that into this class. There's our node, all set to go. Constructor. So there's a QLink class, needs to initialize head to empty, tail to empty, and size to 0. So somebody says add an item. What was the first thing that we did?
Create a node.
Node, next item, next node is new node with item. There's our new node. And then what?
Add to the neighbor list, so
Tail dot next is next node. And
yeah,
then tail has to move one down the list, so tail equals tail dot next. Any special cases?
if you don't have everything on the list yet.
You can't do tail dot next unless tail actually has something. So the special case typical of linked lists is that this thing is empty. So if item count happens to be empty, then what?
Create a dummy node first.
Where are you going to put it? You got head and tail already. So head equals next node, tail equals next node. Item count is now exactly 1, and we're done. So if it's this code says, sorry, we'll call it size, I guess. So if it's the first one on the list, then it's both the head and the tail, right? Because it's the only one on the list. So it's both the start and the end. So we'll hook it up so it's both the start and the end. The count now has to be 1, and we're done. So get rid of the special case, and that leaves the normal case sitting out there. Oh, just make the new node and tack it on to the end. What happens if somebody says remove?
You get
The rule here is always pick out the thing that you're interested in, make a variable for it. E, the item is head. If you just say head, Eclipse complains because
so you need head stored item.
so you need the actual item that's in the node. So we'll go pick out the item that's in the node, we'll return that, and then we'll figure out what we have to do to fix things.
So head equals head dot next.
So skip over it. So if you advance the head pointer, that basically skips over and makes it go away. And
Item count goes down to size.
item count or size has to go down 1. Peak first.
Just compare.
Head dot stored item and return item. What does that say about peaking? Is there something you should do before you peak?
Check to see if there is a node.
Yeah, rule is there has to be at least one item, so if anybody's calling peak, they'd better check size first to make sure that there's one item. The other choice here is that you could make peak return a null in the case where it was empty, but normally people would say you need to check first. Because you're either going to have to check first to make sure you've got something, or you're going to check afterwards to make sure you didn't have a null anyway. So one way or another, you're going to have to check. Peak last. We'll just steal that. Oops. One more time. And that just becomes, the only thing we're interested in is the tail. Size is return the variable called size, which was not the best thing to name it, but that's okay. And that's the entire linked list class for a queue. Okay? So as long as you get this idea of, oh, I've got to put a tail node in here, then this game becomes really, really simple. Okay? While I've got this diagram up, one of the things that most linked list implementations will do is they'll add a backward pointer to all of the nodes. And then they'll make the pointers go in that direction also. Okay? And so quite often with iterators, you'll see like the list iterator provides a special case of iterator. There's actually, instead of the normal iterator, there's the list iterator. And the list iterator allows you to go both forwards and backwards through either a linked list or an array, if you ever have the need to go forwards and backwards. Okay? Any other advantage of playing that game with the backwards pointers?
It's really easy to insert. You know,
How easier to
Well, suppose that we're an iterator, and if we were an iterator and we were sitting here and we didn't have the backward pointer, and somebody said, remember the iterator interface has a remove, how would you do remove if you're standing there and you don't have backward pointers? You got to go way back to the beginning and get to the one before in order to remove the one that you're standing over. Okay? But look what happens if you add a backwards pointer and you're standing on this one and somebody says remove one. All that you have to do to remove is say, oh, I just take one step backwards on that link. There's the one before. Now I'll just link the one before to the one after. Okay? So the biggest advantage of the doubly linked list is that it makes the iterator's remove method really, really, really efficient, because you can always go look at things and remove them. And that's the normal thing that you want to do with lists, right? I'm going to go through all of the people in Comp139 and I'm going to remove everybody who has a mark less than 60. Right? There's that whole filter thing that goes on that people normally do with lists, and so that makes remove a really, really efficient operation, which explains to you why I didn't implement it when we did chained list, why I didn't do the iterators remove, because it was silly to go to the beginning and have to wind your way through to find the one before. But once you have the doubly linked list, then it's really easy. Okay? So the bottom line of this is that once you get this structure, it's easy to add to the end, it's easy to remove from the beginning, and it's easy to remove from the middle with an iterator. Okay? So most linked list implementations that you see will do at least that in order to make things work. Okay. To run the unit tests, all that we would have to do is go into our array test and change this thing. Every time it said Q array, we'll make it Q linked, which, just for the fun of it, let's do it and see how lucky we got. So we'll just replace them all, and we'll save it and run the unit tests. Oops. Got a little bug. What doesn't it like? Oh, this is Q. Got one too many things. Refactor would have been better, huh? And what's my error there? Oop. Don't need that silly import statement. That's Eclipse, slides those in sometimes when you do a copy paste. And let's just run that thing. And for some reason, when we added items, size wasn't going up. So let's just go look in NQ, and there's size plus plus, and save it. Run it again. There we go. So notice there's the joy of the unit test, right? Wrote the code really, really quickly, went, yeah, okay, run the unit test, there's my error, ship it. Assuming we got good unit tests. Okay, so there's neither of those is too difficult to do. Our third option was to implement this queue with either an array list or a linked list underneath it, and do all of the operations in terms of that. Okay, so here's a question for you. If I say, let's use, we've got array list, which has an array underneath. We've got linked list. Okay, so suppose I say with array list, what I'm going to do is I'm always going to add to the 0, and I'm always going, or sorry, remove from the 0 and always add to the n. Not going to work too well. So we're going to basically have to implement this same sort of structure. Okay. What about if we use linked list to do the implementation? What do you do when you want to do an add to the queue? Just add to the end. What if you want to get the first one?
Remove from the head.
Remove from the head. What's linked list going to do if you remove the 0 item? Just goes bzzz, because it's already got a chain of things underneath it. So this thing is the easier and more efficient way probably to, if you just want to do a quick queue, just implement it with linked list underneath, and you know it's going to be efficient, and you don't have to worry about getting your head figuring out wraparound and what array list is trying to do underneath when it grows and all of that sort of nastiness, which would really cause you problems. Okay, so this one becomes the easy implementation for layering on top of. Okay, those are the easy ones. There's a queue. Now we need an example of a queue. Let's talk about CNN.com. So there's the CNN website. For some reason, there's some big world event, and people start checking CNN, the web server, to see what's going on. So it's got to process a whole bunch of requests. Do you think the CNN computer can handle it?
No.
Even if it's an IBM mainframe?
Nope.
Chances are probably no.
DDoS.
Okay? So they don't have enough capacity with one computer to probably be able to process all the requests. But yet there's only one IP address for CNN.com. Okay? What do you think CNN does?
Uses proxy servers to distribute incoming traffic.
So they have a queue of servers waiting.
It just makes a whole bunch of servers. right? So now we've got this big list of however many computers sitting there. So what's the job of the main CNN server now? You've got more than one server here. So what's the first job that it has to do, probably? Picks the least busy one, right? Because remember, not all of these are operating necessarily even operating at the same speed, right? So you pick the least busy of those servers. So you go through the list and you say, how many requests do you have? How many requests do you have? Until you find one that's the least busy. And then you queue up a request there for that server. And then that server is the one that eventually goes back and replies to you in the real world, pretending to be the regular CNN server. Okay? Eventually what happens if it's a big world event, all of these guys start to more or less fill up, and the queues here also start to fill up. Okay? So if it got really, really busy, you would end up with a situation that looked like this. So the goal is, oh, find the least busy server. So what's each one of these servers trying to do? Just bump off these requests as fast as they can, right? So this is a queue of all of the pending requests for this server, so it's just going to go through and try to make this queue smaller, and in the meantime, this guy's coming along and trying to dump requests onto the end. So there's this idea that queues are traditionally this game of, somebody's trying to add requests and externally, and then this computer is just trying to remove the ones that CNN keeps putting on until it's trying to bring it back down to 0. Okay? So what I wanted to do was I wanted to do a simulation of this in Java with exactly this same sort of structure. So I want an array of queues, just to make your life a little bit miserable. And I want one main thing that's basically accepting input. Okay? And so what I did was I've got a main program where I can just type stuff, just random stuff that doesn't have to be URLs, that gets sent into this thing. And then this thing goes through and needs to scan down the list of all of the servers that it's got, find the one that's least busy, and add something onto the end. But that gives me, the one entity on the front that's playing the game of adding things in. I also need something on the back end that tries to remove these things. And if I just do a loop, I can remove them faster than I can type, right? So that doesn't do me any good. So what I did on the back end is I put in a timer. And so I've got a timer class object that's going to play the role of, oh, I'm just going to wake up every so many seconds, and I'm going to go randomly choose one of these and make it go away. Okay? So now I've got two independent entities in the program, me being the monkey on the front end, and something regularly on the back end going, oh, let me find one of these, let me remove a request. Okay? And so we'll set that thing up. Now this one, because it was fairly complicated, rather than boring you, I just wrote the code for it because it's got some sort of interesting things in it on the side. So we'll just go look at the example here, if I can find it. It's this thing called Server Manager that's posted on Git. Get rid of all this old stuff. And let's just go take the thing, and without even looking at it, I'm going to run it, because running it gives you the sense of what it's doing. Okay, so I'm just going to run this thing. And what happens is you're supposed to enter a URL, so I'm just going to type some garbage here. And every time I enter a URL, it gives me a list of all of the servers and how much stuff that they've got pending. Okay? Now, the other thing that's going to have, so we'll just start entering URLs, and you can see that they're being added on to each of these individual guys. And then at some point, the timer starts up, and the timer starts picking random servers out of the queue and saying, oh, okay, dequeue an item. So you can see, even though I'm not typing anything, there's the timer going off at regular intervals, arbitrarily removing stuff. And I can keep typing here and adding stuff, trying to lengthen those queues, right? And it just keeps putting stuff in. And then randomly it will come along, and if you take a look, it's pulled the one out of item 3, right? And it'll just keep doing that until eventually, hopefully, they're all processed. Okay? So it's sort of cool because you get to see user input, you get to see how to do a timer and all of that other sort of good stuff. So now let's have a quick look at the code and see what it does. Okay? So the name of the game typically when you see any of this code is to go say, well, where's the main program? The main program plays this little game here of just calling the constructor. The reason for doing that is that then you get a new, and if you get a new object being created, you don't have to say static on the front of everything in every method that you write in a main program. So that's just a little trick to get a new object. So all of the work here is really sort of done in the constructor. Okay? The idea of the main program is to just show what happens for the, the sort of the high level view of things. So the high level view of things is there's the input loop that says, I'm just going to go and grab a URL from the keyboard. If it happens to be empty, we're done, we'll exit. Otherwise, what we'll do is we'll go find the least busy queue, and we'll add whatever item is onto that server. Okay? And then we'll show the sizes. So that's just the thing that does the printout at the end. Okay? So there's a good idea with main programs, is to just make the ideas really straightforward. Okay? So now you can go pick off all of those. You can pick off the other things. Well, what has to happen when it starts? Oh, well, we need to do a new scanner class to read from the keyboard. So there's how you read from the keyboard the easy way. Make the queues, start the server somehow, which actually really starts the timer, and then go through and continue to do that. Okay. Let's go down and see how you make the queues. This is the fun thing. In the diagram, this thing corresponds to HTTP servers in the code. So that's just really the main thing that tells you where all of the queues are. And its job in the code is to now make an array of however many servers were required. Okay, so this code is a little strange, but see if I can get it all on the screen for you. Just because it's sort of weird. So what this thing does is max servers is the number of servers. This is a weird kind of Javaism for creating an array dynamically instead of filling in the static number in the square brackets, it does basically the same thing. So this says, make me a new array of that type of thing of however many we needed. Okay? Array deck is basically a queue. Okay? So this carves out this piece. So what I end up with is each one of these corresponds to a queue object that I can then talk to. So I can talk to, array decks, or this array sub-zero dot something to get it to respond to a request. That just makes the array. What you have to do when you make an array is that's just an array of nulls. So now you have to make the new for the actual queue object. Okay? This is a weird Javaism. Notice what you give it there is the compiled class. And you remember in in our code, we had to play the same game of saying, oh, okay, now that's an array of that type of thing. Okay, so that initializes all of the Q objects in the array. Okay, so the Qs are all set up. The thing that gets a URL uses the scanner class, and all it does, there's the thing that says, go get me the next line of input. Okay? If there wasn't a line of input, then we're done. If there was a line of input that says quit, we're also done, and we'll return a null. Otherwise, we just take the thing, dump it into a URL object, whatever string they gave. Did the same trick of making a URL object just in case we needed to change it. Okay? So notice again, this code is flat, even for something like user input. Here's the piece of code that finds the least busy server. This is basically the minimum game, right? Pick the first one out of the list and say, this is smallest I've seen so far. Then go through all of the other things that are in the array. Ask that thing for its size. Ask the queue for its size. And if it's smaller than the one that you've got already, then it becomes the smallest one. And notice that I'm picking off the eventually return the index of the least busiest server. Actually, I return the entire queue object. Okay. Show server queues. That one just goes through all of the servers we've got and prints out what ID number they are, plus asks them for their size. Okay, so nothing special there. The fun in this game is getting the timer going. And so if you've never seen how to do a timer in Java, this is how it's done. Java has a timer object. The timer object has a repeat interval, which is a number of seconds, or actually microseconds that I picked off up there. And then you give the timer object something that has an action perform method. Okay, so it follows that sort of GUI style of you make this object and it has the piece of code inside it that's going to be required. Okay. And then you have to do timer.start to get the thing going. Okay? So now the timer is just going to go off at regular intervals. It's going to go take that random serves action listener code, and it's going to run it every time the timer goes off. Okay? So this random serve object action performed gets called every 5 seconds or whatever the interval happens to be. What does it do? It uses a new random object, so there's the use of random to go out and grab an integer that's smaller than the length of the number of items I've got in the array. So it basically picks one of the indexes out of the array, and then it says, oh, okay, if there's actually something that's available, right, or sorry, if there's something in the queue, then just call remove to remove it. Oh, that's interesting. It's a queue. I thought we said NQ and DQ was what we used. Turns out that these guys, for their queue, decided to use add and remove. And I don't like that, because now you can't tell that it's a queue, and you can't tell that add always adds to the end, and that this remove with no arguments always removes the first one. So remove with no arguments removes the first one, remove with any other argument removes a specific one. Oops, but anyway. So they use add and remove. So this thing says, you know, go find if it's actually got something to remove, then remove it and print out what you removed. Okay, and so there's the entire code for that. The timer just pops them off. We missed the add method for adding into the queue. Can't remember where it hit, but that's the entire code. Okay, So this one has a whole lot of goodness in it. If you want to see some interesting things going on, it's fairly sophisticated with timers, user input, action perform method, all sorts of Java sneakiness in there, arrays of objects, right, that you've never seen before. The other thing I'll point out really, really quickly is here's the Q class. Oops, over here. This is the interface for the Java Q class. Notice that there's a whole whack of sub-interfaces, which still don't write code, and then there's actual implementations of queues. The one we're using is that one. This one's a little special because it's a sort of a Swiss Army knife of data structures. It can both be a stack, a queue, various other things, because it's got the linked structure with it. Okay? So that's the one to use, the linked list version. Oh, this is interesting. Linked list can already pretend to be a queue just by using add and remove, add to the end, remove. So it already implements the interface, so you can turn around and use linked list as a queue. Where's array list in there? Why do you think array list, they don't want to make it a queue? What's the thing about array list that makes it difficult to operate as a queue?
You have to check that you don't overrun your head.
Yeah, remember array list does the grow thing if it runs out of room, which totally messes up what you do with the queue. So it just turns out that the reason that they didn't implement it is that this is the easiest one to implement, right? So you just run the linked list queue, and it's really, really easy. Okay? So basically the two choices as far as you're concerned are use the linked list for a queue or use ArrayDec for a queue would be the two normal ones. But the trick is, regardless of which implementation you use, if you declare your thing like I did with Q as the name on the left-hand side, that's the thing that makes it obvious to people that you're only planning on using the add and remove, and you're not planning on using all of the other features of linked list. Okay? And the other thing that's weird about this class is that there's actually two different versions of add, for instance, depending on whether or not you want your program to die for some reason, or whether or not you want to check to make sure there's room before you add. Okay? So the ones that return a special value are the ones that before you use them, before you remove, you can go and check the size to see if there's anything to remove and do the right thing. These, if you try to remove and there's nothing there, then your program dies, which may or may not be what you want. So two special versions that do sort of the same thing. Okay? And with that, we're out of here for today.